Data preprocessing is one crucial step of data science process. Challenges with data, noise and outliers, missing data, inconsistent data, duplicate data, data that is biased, data that is unrepresentative of the phenomenon or population that the data is supposed to describe. These can be overcome by data transformation. Data transformation refers to the process of modifying or manipulating the raw data to make it more suitable or informative for a specific machine learning algorithm or task. Data transformation techniques aim to improve the quality, representation, or distribution of the data, which can lead to better model performance and more accurate predictions. Data transformation can involve various operations, including scaling and normalization. Scaling transforms the data to a specific range, often between 0 and 1 or -1 and 1, to ensure that all features have a similar scale. Normalization adjusts the data distribution to have zero mean and unit variance, making it easier for algorithms to learn from the data. A logarithmic transformation. Applying a logarithmic function to data can help handle skewed distributions and compress large ranges. Logarithmic transformation can make the data more symmetrical and reduce the influence of extreme values. A power transformation. Power transformation, such as the Box-Cox transformation, adjusts the distribution of the data by raising it to a power, lambda. It can help stabilize variance, normalize the data, and make it conform more closely to a normal distribution. Encoding categorical variables. Categorical variables need to be transformed into numerical representations for many machine learning algorithms. This can involve techniques like one-hot encoding, label encoding, or ordinal encoding to represent categorical variables as binary vectors or numerical values. Feature engineering. Feature engineering involves creating new features from existing ones or transforming features to capture more meaningful patterns or relationships in the data. This can include operations like polynomial features, interaction terms, or creating domain-specific features. Handling missing values. Data transformation techniques can be used to handle missing values and noise in the dataset. This can involve imputation methods such as mean, median, or mode imputation, or more advanced techniques like multiple imputation or regression imputation. Dimensionality reduction. Data reduction, reduce data size by, for instance, aggregating, eliminating redundant features, or clustering. And dimensionality reduction techniques like principal component analysis, PCA, or singular value decomposition, SVD, transform high-dimensional data into a lower-dimensional representation while retaining the most important information. This can help reduce computational complexity and remove noise or redundant features. Data integration merges data from multiple sources into a coherent data store, such as a data warehouse. The choice of data transformation techniques depends on the specific characteristics of the data, the requirements of the machine learning algorithm, and the nature of the problem at hand. It is important to carefully analyze and understand the data before applying transformations to ensure that they align with the goals and assumptions of the machine learning task. Data cleaning. This section is for data cleaning and for data quality improvement. Handling missing value. Missing data mechanisms are typically classified as one of the following: MCAR, missing completely at random; MAR, missing at random, or MNAR, missing not at random. This one tough to handle. It is extremely difficult to determine the cause for this type of missing data if you do not have any background knowledge on how the data is generated. Steps to manage missing data. Ignore the tuple. Used when the class label is missing in a classification task. Not very effective, unless the tuple contains several attributes with missing values. A poor technique when the percentage of missing values per attribute varies considerably. By ignoring the tuple, we do not make use of the remaining attributes' values in the tuple. Such data could have been useful to the task at hand. Fill in the missing value manually. Time-consuming. May not be feasible given a large data set with many missing values. Use a global constant to fill in the missing value. Replace all missing attribute values by the same constant, such as a label like unknown or -1. If missing values are replaced by, say, unknown, then the mining program may mistakenly think that they form an interesting concept, since they all have a value in common, that of unknown. Hence, although this method is simple, it is not foolproof. Use a measure of central tendency for the attribute and perform mean/median imputation. Used for MCAR/MAR. Central tendency indicates the middle value of a data distribution. e.g. mean or median. For normal, symmetric data distributions, the mean can be used. A skewed data distribution should employ the median. Use the attribute mean or median for all samples belonging to the same class as the given tuple. For example, if classifying customers according to credit risk, we may replace the missing value with the mean income value for customers in the same credit risk category as that of the given tuple. And if the data distribution for a given class is skewed, the median value is a better choice. Use the most probable value to fill in the missing value. This may be determined with regression inference-based tools using a Bayesian formalism or decision tree induction. For example, using the other customer attributes in the dataset, we may construct a decision tree to predict the missing values for income. Most popular strategy. Important Python pandas missing values handling functions are null, not null, dropna, fillna, replace, interpolate. Handling noisy value. Noise is a random error or variance in a measured variable. Outliers may represent noise. Basic statistical description techniques, e.g., boxplots and scatterplots, and data visualization can be used to identify outliers. Noisy data can be removed by using smoothing techniques. Smoothing. Data smoothing in machine learning refers to the process of reducing noise or variability in a dataset to reveal underlying patterns or trends. It involves applying a smoothing technique to the data to create a simplified representation that is easier to analyze or work with. The goal of data smoothing is to remove random fluctuations or outliers while preserving the overall structure and important features of the data. There are several commonly used techniques for data smoothing. O-binning. O-smoothing by bin means. O-smoothing by bin medians. The binning techniques reduce the number of distinct values per attribute. This acts as a form of data reduction for logic-based data mining methods, such as decision tree induction, which repeatedly makes value comparisons on sorted data. Moving average. This method calculates the average of a fixed window of data points and replaces each data point with the computed average. Moving averages can be simple, unweighted, or weighted, where more recent points are given higher weights. Moving averages are effective in reducing short-term fluctuations and highlighting long-term trends. Exponential smoothing. This technique assigns exponentially decreasing weights to older data points and higher weights to more recent data points. Exponential smoothing is particularly useful for time series data, as it gives more importance to recent observations while still considering past observations. Savitsky-Golay filter. This method uses a sliding window of data points and fits a polynomial function to the window. The polynomial coefficients are then used to smooth the data by averaging the values predicted by the polynomial. The Savitsky-Golay filter is often used for smoothing noisy signals and is especially effective for removing high-frequency noise. A kernel smoothing. Kernel smoothing, also known as kernel density estimation, applies a smoothing function kernel to each data point and averages the results to obtain a smoothed representation. The kernel function determines the weights assigned to neighboring data points, with closer points receiving higher weights. Common kernel functions include Gaussian, triangular, and Epinechnikov kernels. LOES, locally weighted scatterplot smoothing. This technique fits a regression line to localize subsets of the data using weighted least squares. It assigns higher weights to points that are closer to the target point being smoothed. LOES is effective in capturing nonlinear relationships and is often used for scatterplot smoothing. Data smoothing can be useful in various scenarios, such as noise reduction, trend identification, and outlier detection. However, it's important to note that data smoothing alters the original data and may introduce some degree of distortion or loss of information. The choice of the smoothing technique should be based on the characteristics of the data and the specific objectives of the analysis or modeling task. Outlier analysis. Outlier analysis in machine learning refers to the process of identifying and handling outliers in a dataset. Outliers are data points that significantly deviate from the normal or expected patterns in the data. They can arise due to measurement errors, data corruption, or genuinely rare events. Detecting and handling outliers is important because they can have a significant impact on statistical analysis and machine learning models. Outliers can distort the data distribution, affect parameter estimates, and introduce bias in model predictions. Therefore, it is necessary to identify and handle outliers appropriately. Here are some common approaches for outlier analysis in machine learning. Visualization. Plotting the data can be a useful first step in identifying outliers. Box plots, scatter plots, histograms, or density plots can reveal any data points that are far away from the majority of the data. Visual inspection can help detect extreme values or unusual patterns. Statistical methods. Z-score. Z-score measures how many standard deviations a data point is away from the mean. Data points with z-scores above a certain threshold, e.g. 2 or 3, can be considered outliers. IQR, interquartile range. The IQR is the range between the 25th and 75th percentiles of the data. Data points outside a certain range, e.g. 1.5 times the IQR, can be classified as outliers. Distance-based methods. Euclidean distance. Data points that are far away from the centroid or mean of the data can be considered outliers. We can use k-mean clustering methods or density-based clustering methods for this. Mahalanobis distance. Mahalanobis distance considers the covariance structure of the data. Data points with high Mahalanobis distances are considered outliers. Machine learning techniques. Clustering. Outliers may form separate clusters or be assigned to sparsely populated clusters. By clustering the data, outliers can be identified as points that do not belong to any cluster or belong to small clusters. Anomaly detection. Anomaly detection algorithms, such as isolation forest, one-class SVM, or autoencoders, are specifically designed to identify outliers or anomalies in data. These algorithms learn the normal patterns in the data and flag instances that deviate significantly from those patterns. Once outliers are identified, you can choose to handle them in various ways depending on the specific situation. Removal. You can remove outliers from the dataset if they are the result of measurement errors or data corruption. Transformation. Applying transformations such as logarithmic, square root, or Box-Cox transformations can help normalize the data and reduce the impact of outliers on subsequent analysis or modeling. It's important to note that outlier analysis is often problem-specific, and the choice of methods and thresholds can vary depending on the context and domain knowledge. It is recommended to carefully assess the impact of outliers on the analysis or modeling task and choose appropriate strategies accordingly. Other methods: regression, data discretization, and data reduction. Data aggregation. Aggregation is combining two or more objects into a single object. Consider a dataset consisting of transactions, data objects, recording the daily sales of products in various store locations, Minneapolis, Chicago, Paris, for different days over the course of a year. One way to aggregate transactions for this dataset is to replace all the transactions of a single store with a single store-wide transaction. This reduces hundreds or thousands of transactions that occur daily at a specific store to a single daily transaction. The number of data objects is reduced to the number of stores. To create the aggregate transaction that represents the sales of a single store or date. Quantitative attributes, such as price, are typically aggregated by taking a sum or an average. A qualitative attribute, such as item description, can either be omitted or summarized as the set of all the items that were sold at that location. The data in the table can also be viewed as a multidimensional array, where each attribute is a dimension. From this viewpoint, aggregation is the process of eliminating attributes, such as the type of item, or reducing the number of values for a particular attribute, e.g., reducing the possible values for date from 365 days to 12 months. This type of aggregation is commonly used in online analytical processing, OLAP. First, the smaller datasets resulting from data reduction require less memory and processing time. This allows the use of more expensive data mining algorithms. Second, aggregation provides a high-level view of the data instead of a low-level view. E.g., aggregating over store locations and months gives us a monthly per store view of the data instead of a daily per item view. Finally, the behavior of groups of objects or attributes is often more stable than that of individual objects or attributes. This statement reflects the statistical fact that aggregate quantities, such as averages or totals, have less variability than the individual objects being aggregated. The disadvantage of aggregation is the potential loss of interesting details. In the store example, aggregating over months loses information about which day of the week has the highest sales. Sampling. Data sampling refers to the process of selecting a subset of data from a larger population or dataset for analysis or modeling purposes. It involves taking a representative portion of the data to make inferences or draw conclusions about the entire population. The selected subset, known as a sample, should ideally possess similar characteristics and statistical properties as the original dataset. Data sampling is needed for several reasons. Efficiency. Working with the entire dataset may be computationally expensive and time-consuming, especially when dealing with large volumes of data. Sampling allows analysts to work with a smaller subset, reducing computational requirements and speeding up the analysis process. Cost-effectiveness. In some cases, collecting data for an entire population might be impractical or costly. Sampling allows researchers to gather information from a representative sample at a fraction of the cost, while still providing meaningful insights. Inference and generalization. By selecting a representative sample, analysts can make inferences about the entire population. Statistical techniques allow for generalizing the findings from the sample to the larger population, making it possible to draw conclusions with a certain level of confidence. Exploration and analysis. Sampling allow analysts to explore and analyze subsets of data to gain insights and discover patterns or relationships. By examining a manageable portion of the data, researchers can focus their efforts on specific areas of interest. Experimentation. In experimental studies, sampling is used to randomly assign participants or subjects to different groups or treatments. This randomization helps ensure that the groups are comparable, reducing bias and increasing the reliability of the results. It is important to note that proper sampling techniques should be used to ensure the sample is representative and unbiased, minimizing the risk of introducing errors or drawing incorrect conclusions. Statistical methods such as random sampling, stratified sampling, or cluster sampling are commonly employed to achieve reliable and accurate results. Types of data sampling. There are several types of data sampling techniques that can be used depending on the nature of the data and the objectives of the analysis. Here are some commonly used data sampling methods. Simple random sampling. This is the most basic form of sampling, where each observation in the population has an equal chance of being selected. In simple random sampling, a subset of data is selected entirely by chance. It ensures that each element in the population has an equal probability of being included in the sample, making it representative. Random number generators or lottery methods are commonly used to implement this technique. Sampling. In stratified sampling, the population is divided into subgroups or strata based on certain characteristics that are relevant to the analysis. Then, a random sample is taken from each stratum in proportion to its size. This technique ensures that the sample accurately represents the characteristics of each subgroup in the population. Stratified sampling is useful when the population is heterogeneous and contains distinct groups. Cluster sampling. Cluster sampling involves dividing the population into clusters or groups, typically based on geographical proximity or other similarities. A few clusters are selected randomly, and all elements within the selected clusters are included in the sample. This technique is efficient when it is difficult or impractical to sample individuals directly and when clusters are relatively homogeneous. It is commonly used in surveys and studies involving geographically dispersed populations. Systematic sampling. In systematic sampling, a starting point is randomly selected from the population, and then every nth element is included in the sample. For example, if every 10th element is selected, the first element is randomly chosen, and then every 10th element thereafter is included. This method provides a systematic and straightforward approach to sampling, especially when the population is ordered in some way, such as a list of customers or time series data. Convenience sampling. Convenience sampling involves selecting the most readily available individuals or data points for the sample. This technique is convenient and quick, but it may introduce biases and lack representativeness. Convenience sampling is often used for exploratory or preliminary analysis when time or resource constraints limit the possibility of more rigorous sampling methods. It should be used with caution, as the results may not be generalizable to the larger population. Snowball sampling. Snowball sampling is a technique where initial participants or data points are selected, and then additional participants are recruited based on referrals from the initial participants. This method is commonly used when studying hard-to-reach or hidden populations where traditional sampling methods are not feasible. Snowball sampling relies on social networks and can be effective for accessing individuals who share certain characteristics or experiences. These are just a few of the many sampling techniques available, and the choice of sampling method depends on the specific research objectives, available resources, and the characteristics of the population being studied. It is important to carefully consider the strengths, limitations, and potential biases associated with each sampling method to ensure the sample is representative and the analysis is reliable. Sample size. Determining the right sample size for a data sample involves considering various factors such as the desired level of confidence, margin of error, variability in the population, and available resources. Here are 3 commonly used formulas for determining sample size. Sample size for proportions. The formula to calculate the sample size needed for estimating proportions is n equals z squared times p times q slash e squared, where n, sample size needed, as z-score corresponding to the desired confidence level, e.g., 1.96 for 95% confidence level. P, estimated proportion or expected prevalence in the population. Q, complement of P1P. E, margin of error or acceptable level of sampling error. This formula provides an estimate of the sample size required to estimate a population proportion with a specific level of confidence and margin of error. Sample size for means. The formula to calculate the sample size needed for estimating population means is n equals z squared asterisk sigma caret 2 slash e squared, where n, sample size needed, as z-score corresponding to the desired confidence level, e.g., 1.96 for 95% confidence level. Sigma, standard deviation of the population, if unknown, an estimate from a pilot study or previous research can be used. E, margin of error or acceptable level of sampling error. This formula provides an estimate of the sample size required to estimate a population mean with a specific level of confidence and margin of error. Sample size for regression or hypothesis testing. The formula to calculate the sample size needed for regression analysis or hypothesis testing is more complex and depends on several factors, including the desired statistical power, effect size, and significance level. The formula generally takes the form n equals z underscore alpha slash 2 plus z underscore beta, caret 2 asterisk, sigma caret 2 forward slash, delta caret 2, where n, sample size needed, z underscore alpha slash 2, z-score corresponding to the desired significance level, e.g., 1.96 for 95% significance level. Z underscore beta, z-score corresponding to the desired statistical power, e.g., 0.84 for 80% power. Sigma, standard deviation of the population, if unknown, an estimate from pilot study or previous research can be used. Delta, effect size, difference in means or regression coefficient. This formula provides an estimate of the sample size required to achieve a desired statistical power for hypothesis testing or regression analysis. It's important to note that these formulas provide approximate sample size estimates and assumptions about the population distribution are often made. Additionally, other considerations such as practical constraints, budget, and time limitations may also influence the determination of the sample size. Consulting with a statistician or using sample size calculators and software can help ensure accurate and appropriate sample size determination for specific research studies. Data discretization, also known as binning, is the process of dividing continuous or numerical data into discrete intervals. It involves transforming a continuous variable into a categorical variable by creating bins or intervals that represent a range of values. Each bin or interval represents a specific range or category, and data points falling within that range are assigned to the corresponding category. This is often used for several reasons. Simplification. Discretizing continuous data simplifies the analysis by reducing the complexity of the data. Instead of dealing with many unique values, discrete intervals provide a manageable and more structured representation. A categorical analysis. Discretized data allows for categorical analysis, where data points are grouped into categories or bins. This enables the use of categorical techniques such as frequency analysis, cross-tabulation, and chi-square tests. Privacy and anonymization. Discretizing data can help protect individual privacy by concealing specific values or reducing the level of granularity. For example, age or income data can be discretized into age groups or income brackets to preserve privacy while still allowing for analysis. Handling skewed distributions. Discretization can help address issues related to data distribution, especially when dealing with highly skewed or long-tailed distributions. By grouping values into intervals, it can mitigate the impact of extreme values or outliers and provide a more balanced representation of the data. There are different techniques for discretization, including equal width binning. In this method, the range of the data is divided into a predetermined number of equal width intervals. Each interval has the same width or range, and data points falling within that range are assigned to the corresponding bin. Equal frequency binning. In this approach, the data is divided into intervals such that each bin contains approximately the same number of data points. This method helps ensure an equal distribution of data across the intervals, regardless of the value range. A clustering-based discretization. This technique involves using clustering algorithms, such as k-means or hierarchical clustering, to group similar data points together. The resulting clusters are then treated as discrete categories. A domain knowledge-based discretization. Domain experts or subject matter specialists may define the bins or intervals based on their knowledge of the data and its characteristics. This approach allows for more customized discretization based on specific requirements and insights from the domain. Entropy-based data discretization is a technique that utilizes the concept of entropy from information theory to determine the optimal cutoff points or intervals for data discretization. The goal is to find the boundaries that minimize the entropy or maximize the information gain when dividing the continuous variable into discrete categories. The formula used in entropy-based data discretization is called the information gain formula or the entropy formula. It calculates the entropy of a dataset or a subset of data, which represents the level of impurity or randomness in the data. The formula is as follows. Entropy D equals sigma pi asterisk log 2 pi, where entropy D is the entropy of the dataset D. Pi represents the probability of occurrence for each category or class I within the dataset. The summation sigma is taken over all the categories or classes in the dataset. The information gain can be calculated by comparing the entropy of the original dataset to the entropy after splitting the data based on a particular attribute or cutoff point. The attribute or cutoff point that results in the highest information gain is selected as the optimal choice for data discretization. The information gain formula and entropy-based discretization aim to find the best split or boundaries that maximize the homogeneity within each category while maximizing the difference between categories. It seeks to achieve the most informative and meaningful representation of the data with minimal information loss. It's important to note that entropy-based data discretization can be used in various algorithms and approaches, such as decision trees, e.g., ID3, C4.5, where it is often employed to determine the optimal splits at internal nodes of the tree. Other related techniques, such as gain ratio or Gini index, may also be used in conjunction with entropy to assess the quality of splits during data partitioning. The choice of discretization technique depends on the nature of the data, its distribution, and the objectives of the analysis. It is essential to consider the trade-offs between granularity and information loss, as well as the impact of discretization on subsequent analysis or modeling tasks. Data binarization. Data binarization, also known as thresholding or binarizing, is a process of converting continuous or numerical data into binary or categorical data. In this process, a threshold value is chosen, and any data point above or equal to the threshold is assigned one category or value, e.g. 1 or yes, while data points below the threshold are assigned another category or value, e.g. 0 or no. Binarization is often used for several purposes. Simplification. Binarizing data simplifies the analysis by reducing the complexity of continuous variables into discrete categories. It transforms a range of values into a binary representation, making it easier to work with and interpret. Feature engineering. Binarization can be a part of feature engineering, where continuous features are transformed into binary features to represent certain characteristics or patterns in the data. For example, converting a temperature variable into hot or cold based on a threshold. Thresholding. Binarization allows for thresholding, where specific values or conditions are of interest. By defining a threshold, the focus is on whether a data point meets or exceeds that threshold, rather than the specific value itself. Classification. Binarization is often used as a pre-processing step for certain classification algorithms that require binary input. By converting continuous data into binary form, it allows for the application of algorithms that can only handle binary features. The choice of the threshold value in binarization depends on the specific problem, domain knowledge, or statistical considerations. It can be a fixed value determined based on specific requirements or can be dynamically determined using techniques like Otsu's method or adaptive thresholding. It's important to note that binarization leads to information loss as it reduces the continuous nature of the data into binary categories. Care should be taken when binarizing data, as the choice of threshold can impact the subsequent analysis or modeling tasks. Data normalization. standardization, feature scaling. Feature scaling and data normalization are techniques used to transform the values of features in a dataset to a specific range or distribution. These techniques are applied to ensure that all features have similar scales and to normalize the data, making it easier for machine learning algorithms to learn from the data effectively. Algorithms those are impacted by improper scaled data are followings: O-linear and logistic regression, O-neural networks, O-support vector machines, OKNN, O-k-means clustering, O-linear discriminant analysis, LDA, O-principal component analysis, PCA. Feature scaling. Feature scaling is a method used to standardize the range of values of different features in a dataset. It ensures that all features have a similar scale, preventing certain features from dominating the learning process based solely on their larger values. Common techniques for feature scaling include eta normalization. Eta normalization is a technique used to adjust the distribution of the data to a specific form, often a normal distribution or a standard distribution. It helps to handle skewed or non-uniform data distributions. Different types of data normalization techniques include min-max scaling, normalization. Min-max scaling, also known as normalization, scales the features to a specific range, typically between 0 and 1. It transforms the data using the following formula: x underscore scaled equals x underscore min / x underscore max x underscore min, where x underscore scaled is the scaled value, x is the original value, x underscore min is the minimum value in the feature, and x underscore max is the maximum value in the feature. Standardization. Z-score scaling. Standardization transforms the data to have zero mean and unit variance. It subtracts the mean of the feature and divides it by the standard deviation. The formula for standardization is as follows: x underscore scaled equals x underscore mean / x underscore std, where x underscore scaled is the scaled value, x is the original value, x underscore mean is the mean of the feature, and x underscore std is the standard deviation of the feature. Decimal scaling. Decimal scaling normalizes the data by shifting the decimal point of each value, just divide by 10. The decimal point is moved to the left by a factor such that the largest absolute value becomes less than 1. Log transformation. Log transformation is used to handle skewed distributions by applying a logarithmic function to the data. It compresses the range of values, reduces the impact of extreme values, and makes the data distribution more symmetrical. These are some of the commonly used techniques for feature scaling and data normalization. The choice of the technique depends on the characteristics of the data and the requirements of the machine learning algorithm being used. Handling categorical data in coding. This is the process of transforming categorical variables into numerical representations that can be used as inputs for machine learning algorithms. This transformation is necessary because most machine learning models are designed to work with numerical data. Here are several common methods for this. 1. Hot encoding. Each category is converted into a binary vector representation. For each categorical feature, a new binary feature is created for each unique category. The value 1 is assigned to the corresponding category, and 0 is assigned to all other categories. This method works well when the number of categories is small and there is no hierarchical or ordinal relationship among them. One potential issue with one-hot encoding is the creation of high-dimensional feature spaces if the categorical variable has many unique categories. Label encoding. Each category is assigned a unique integer label. The labels are assigned based on the order of appearance or some predefined order. This method is suitable when there is an ordinal relationship among the categories, as it preserves the order. It may introduce unintended relationships between categories that could impact the model's performance. Ordinal encoding. Each category is assigned a numerical value based on its rank or order. The assigned values represent the relative order or priority of the categories. This encoding is useful when the categories have an inherent order or rank, such as low, medium, high. The assigned values should be chosen carefully to ensure they reflect the underlying relationship accurately. Count encoding. Each category is replaced with the count of occurrences of that category in the dataset. This method can be helpful when the frequency or prevalence of a category is informative for the target variable. It reduces the dimensionality of the categorical feature space, but may not capture the intrinsic relationship between categories. Target encoding, mean encoding. Each category is replaced with a mean, or other aggregated statistic, of the target variable for that category. This method captures the relationship between the categorical variable and the target variable. It can be susceptible to overfitting, especially when the number of samples per category is small. Binary encoding. Each category is encoded as a binary code. The categories are first converted into ordinal values, and then each ordinal value is represented in binary format. This method reduces the dimensionality of the categorical feature space compared to one-hot encoding while preserving some information. Hash encoding. Each category is hashed into a fixed number of features. The hashing process converts the categories into numerical representations. This method is useful when memory or computational resources are limited, as it can handle many categories efficiently. However, collisions may occur, where different categories are mapped to the same hash value. Text preprocessing. Text preprocessing is an essential step in NLP that involves transforming raw text data into a format suitable for analysis and modeling. Here are the common text preprocessing steps. Tokenization. Breaking the text into individual words or tokens. This step splits sentences into words, removing punctuation and special characters. Tokenization forms the basis for further analysis. In NLP, tokens refers to the total number of words in your corpus. I put words in quotes because the definition varies by task. The vocab is the number of unique words. Lowercasing. Converting all text to lowercase. This step ensures that words with the same letters but different cases are treated as the same word. For example, apple and apple become identical after lowercasing. Stop word removal. Removing common words stop words that do not contribute much to the overall meaning of the text. Examples of stop words include the is, and etc. Removing stop words helps reduce noise and focus on more important words in the text. Remove punctuation. Removing special characters, such as punctuation marks, symbols, and non-alphanumeric characters, which are not relevant to the analysis. This step simplifies the text and reduces noise. Numeric character removal. Removing numeric digits from the text. Numbers may not carry much meaning in certain NLP tasks, such as sentiment analysis or topic modeling. Removing numbers can simplify the text and improve processing efficiency. Lemmatization or stemming. Reducing words to their base or root form. Lemmatization aims to transform words to their meaningful base form, called a lemma, e.g. running to run, while stemming reduces words to a common stem by removing prefixes or suffixes, e.g., running to run. This step helps in consolidating similar word forms and reducing vocabulary size. Part of speech, POS, tagging. Assigning grammatical tags to words in the text, such as nouns, verbs, adjectives, etc. POS tagging helps in understanding the syntactic structure of the text and can be useful for certain NLP tasks. POS tagging is an important natural language processing application used in machine translation, word sense disambiguation, question answering parsing, and so on. The genesis of POS tagging is based on the ambiguity of many words in terms of their part of speech in a context. There are different approaches to performing part of speech, POS tagging, which is the process of assigning grammatical tags to words in a text. Here are some common approaches used in POS tagging. Rule-based approach. This approach involves defining a set of rules based on linguistic patterns or heuristics to determine the POS tags of words. These rules can be handcrafted or derived from linguistic knowledge. For example, a rule might state that if a word ends with ing, it is likely a verb. While rule-based approaches are interpretable and can be effective for specific domains or languages, they can be time-consuming to develop and may not capture all linguistic nuances. Corpus-based/learning-based approach. This approach relies on annotated corpora, large collections of text with manually assigned POS tags, for training machine learning models. Various supervised learning algorithms, such as hidden Markov models, HMMs, or conditional random fields, CRFs, maximum entropy Markov model, MEMM, are commonly used to learn the statistical patterns between words and their corresponding POS tags. These models generalize from the annotated data to tag unseen text. Corpus-based approaches are effective in capturing contextual information and can handle various languages and domains. Dictionary-based approach. In this approach, a dictionary or lexicon containing words and their associated POS tags is used. The POS tag for a given word is looked up in the dictionary. This approach works well for words with consistent POS tags. However, it may struggle with ambiguous words or out-of-vocabulary words that are not present in the dictionary. Hybrid approach. This approach combines multiple methods to achieve more accurate POS tagging. It may involve using rule-based methods as a first pass to tag words with high confidence, followed by statistical models to handle the remaining words. Hybrid approaches aim to leverage the strengths of different methods to improve overall performance. Deep learning approach, such as recurrent neural networks or transformer models, have also been applied to POS tagging. These models learn to capture complex patterns and dependencies in the text automatically. They have shown promising results in achieving high accuracy for POS tagging tasks, especially when large amounts of annotated data are available. The choice of approach depends on factors such as the availability of annotated data, computational resources, the size and nature of the text corpus, and the specific requirements of the application. Different approaches may be suitable for different scenarios, and researchers often experiment with various methods to find the most effective approach for a given POS tagging task. Use of POS tagging. POS tagging is a NLP technique used to assign grammatical tags to words in a text. These tags represent the word's syntactic category, such as noun, verb, adjective, or adverb. POS tagging has several important uses and applications, including text analysis and information retrieval. POS tagging helps in understanding the structure and meaning of a sentence. It provides valuable information about the role and function of words within a sentence, allowing for more accurate text analysis and information retrieval. Parsing and syntax analysis. POS tags are often used as input in syntactic parsers that analyze the grammatical structure of sentences. By providing POS tags, parsers can generate parse trees or dependency graphs, which represent the relationships between words and their syntactic roles. Machine translation. POS tagging is crucial in machine translation systems. It helps to disambiguate words with multiple meanings and assists in selecting appropriate translations based on the grammatical context. POS tags are used as features in statistical translation models. Named entity recognition. POS tagging can aid in identifying named entities, such as names of people, organizations, locations, or dates, within a text. By combining POS tags with other NER techniques, it becomes easier to extract and classify these entities accurately. Information extraction. POS tagging plays a significant role in information extraction tasks, where specific information needs to be extracted from unstructured text. By identifying the part of speech of words, it becomes possible to recognize patterns and extract relevant information, such as identifying verbs or nouns related to a particular topic. Sentiment analysis. POS tagging can contribute to sentiment analysis by providing insights into the sentiment-bearing words in a sentence. It helps in distinguishing positive, negative, or neutral words, allowing sentiment analysis models to understand the sentiment expressed in the text. Grammar and language learning. POS tagging can be used to enhance language learning applications. By highlighting the parts of speech in a sentence, learners can better understand the grammatical structure and rules of a language. POS tagging challenges. While POS tagging is a valuable technique in NLP, it does come with certain challenges. Some of the common challenges in POS tagging include ambiguity. Words in natural language often have multiple possible parts of speech depending on the context. For example, the word run can be a verb, e.g., I run, or a noun, e.g., I went for a run. Resolving such ambiguities accurately can be challenging. Out-of-vocabulary words. POS taggers rely on predefined tag sets and dictionaries. When encountering words that are not present in the training data or the tagger's vocabulary, it becomes difficult to assign appropriate tags. This is particularly problematic for newly coined words, proper nouns, or domain-specific terms. Word sense disambiguation. Many words in natural language have multiple senses or meanings. POS tagging alone may not be sufficient to disambiguate the correct sense of a word. Additional techniques, such as word sense disambiguation algorithms or context analysis, may be required to accurately assign the correct POS tag. Morphological variation. Words in different forms, such as inflections, conjugations, or derivations, may have different POS tags. POS taggers need to handle these morphological variations to accurately assign the appropriate tags. For example, run verb and running noun have different tags despite being related. Tagging ambiguity. Even when the correct POS tag for a word is known, there can be multiple valid tags that represent the same part of speech. For example, both NN and NNS can represent a noun, with NN denoting singular and NNS denoting plural. Choosing the most appropriate tag in such cases can be challenging. Syntactic ambiguity. Certain sentences or phrases can be syntactically ambiguous, making it difficult to determine the correct POS tags. For instance, in the sentence "time flies like an arrow," flies can be either a noun or a verb, leading to different interpretations. Tagging errors propagation. If an initial POS tagging error occurs in a sentence, it can propagate and affect subsequent analysis or applications relying on POS tags. Such errors can degrade the performance of downstream tasks like parsing or information extraction. Addressing these challenges often involves leveraging contextual information, employing machine learning algorithms, and incorporating linguistic rules. Hybrid approaches that combine statistical models with rule-based methods or leveraging contextual embeddings have shown promise in improving the accuracy of POS tagging. However, achieving perfect POS tagging accuracy remains an ongoing research area in NLP. Machine learning techniques, supervised algorithms, such as hidden Markov models, conditional random fields, or neural networks, can be trained on large annotated datasets to learn patterns and improve POS tagging accuracy. These models can capture contextual and syntactical dependencies to make better tagging decisions. Entity recognition, identifying and classifying named entities, such as person names, locations, organizations, dates, etc., in the text. This step helps in extracting specific information from the text and can be crucial for tasks like information extraction or question answering. The named entity recognition is one of the most popular data pre-processing tasks. It involves the identification of key information in the text and classification into a set of predefined categories. An entity is basically the thing that is consistently talked about or referred to in the text. At its core, NLP is just a two-step process. Detecting the entities from the text, classifying them into different categories. There are several techniques used for NER, which is the task of identifying and classifying named entities in text. Here are some commonly used NER techniques. Rule-based systems, using handcrafted rules and patterns to identify named entities based on specific linguistic patterns or characteristics. These rules may include regular expressions, POS tag patterns, context rules, or dictionary lookups. Rule-based systems are often language-specific and require linguistic expertise to develop. While they can be effective for certain domains or languages, they may lack generalization and struggle with handling complex or ambiguous cases. Statistical machine learning. This approach involves training machine learning models on annotated NER data. Supervised learning algorithms, such as conditional random fields, hidden Markov models, or support vector machines, are commonly used. These models learn statistical patterns between words and their corresponding entity labels from the training data. Features used can include word representations, POS tags, context, or neighboring words. Statistical machine learning approaches are effective in capturing contextual information and can handle various languages and domains. Named entity recognition using deep learning techniques, such as RNN or transformer-based models, have shown promising results. These models can learn complex patterns and dependencies in the text automatically without relying on handcrafted rules. They can capture both local and global context, improving the accuracy of NER. Architectures like bidirectional LSTM with conditional random fields and BERT have achieved state-of-the-art performance in NER tasks. Semi-supervised and unsupervised approaches. NER techniques that utilize unlabeled or limited labeled data fall under this category. Semi-supervised methods leverage a combination of annotated and unlabeled data to improve NER performance. Unsupervised methods aim to discover patterns and entities in text without relying on labeled data. These approaches often involve techniques such as clustering, bootstrapping, or distance supervision. While these methods can be useful in scenarios where labeled data is scarce, they may have lower precision and require additional checks. Transfer learning. Transfer learning techniques utilize pre-trained models on large-scale tasks, such as language modeling or masked language modeling. These models capture rich language representations and can be fine-tuned for NER tasks with a smaller labeled dataset. Models like BERT, GPT, or Roberta have been successfully applied to NER tasks, demonstrating improved performance. The choice of NER technique depends on factors such as the availability of labeled data, computational resources, the size and nature of the text corpus, and the specific requirements of the application. Combining multiple techniques or adopting hybrid approaches is also common to achieve better NER performance in different contexts. Spell checking/correction. Correcting misspelled words in the text. Spell checking algorithms can help improve the accuracy of NLP models and ensure correct interpretation of the text. Text normalization. Normalizing text by standardizing abbreviations, acronyms, or variations of words. For example, converting don't to do not or USA to United States of America. Text normalization helps reduce vocabulary size and ensures consistent representation of words. These steps may not be necessary or relevant for all NLP tasks, and the order of these steps can vary depending on the specific requirements. It is important to consider the characteristics of the data and the objectives of the analysis when deciding which pre-processing steps to apply. Parsing. Parsing plays a crucial role in NLP text pre-processing by analyzing the grammatical structure of sentences and extracting meaningful information. Using POS tagging, we might get the below result for the blue umbrella. Determiner, blue, adjective, umbrella, noun. But it is nowhere mentioned blue is used for umbrella. Hence, we need some sort of grouping so as to retrieve the relationship between the words of a sentence. For example, an adjective and a noun might combine to be a noun phrase, the blue umbrella, which might combine with another adjective to form another noun phrase, e.g. the torn blue umbrella. Here are some key use cases of parsing in NLP text preprocessing. Syntactic parsing. Syntactic parsing, also known as parsing for constituency or phrase structure, involves analyzing the syntactic structure of sentences. It identifies the hierarchical relationships between words and phrases, determining how they combine to form meaningful units. Syntactic parsing can be useful for tasks such as grammar checking, syntactic analysis, and understanding sentence structure. Dependency parsing. Dependency parsing focuses on identifying the relationships between words in a sentence in terms of directed links, where one word is the head of another word. These dependencies represent the grammatical and semantic relationships between words. Dependency parsing is essential for tasks such as information extraction, semantic role labeling, and relation extraction. Semantic parsing. Semantic parsing involves mapping natural language expressions to formal representations of meaning, such as logical forms or knowledge graphs. It aims to capture the underlying semantics and intentions of sentences. Semantic parsing is used in question answering systems, chatbots, and natural language interfaces to understand user queries and generate appropriate responses. Error detection and correction. Parsing can be utilized to identify and correct grammatical errors in text. By analyzing the syntactic structure of sentences, parsers can detect inconsistencies, missing or extra words, and incorrect word order. This helps in improving the quality and accuracy of text by suggesting appropriate corrections. Information extraction. Parsing can assist in extracting specific information from unstructured text. By identifying the grammatical structure and relationships within sentences, parsers can extract entities, attributes, and relations between entities. This is useful for tasks such as named entity recognition, relation extraction, and event extraction. Machine translation. Parsing is used in machine translation systems to analyze the syntactic structure of sentences in the source language and generate grammatically correct translations in the target language. Parsing helps in capturing the appropriate word order, sentence structure, and grammatical transformations required for accurate translation. Overall, parsing is a fundamental component of NLP text preprocessing that enables the analysis of sentence structure, identification of relationships between words, and extraction of meaningful information. It facilitates various NLP tasks such as syntactic analysis, semantic understanding, error detection and correction, information extraction, and machine translation. In natural language processing, NLP, parsing refers to the process of analyzing the grammatical structure of sentences and determining how words and phrases relate to one another. It involves identifying the syntactic relationships between words, such as subject-verb, noun modifier, or object-preposition relationships. Parsing aims to understand the hierarchical structure of sentences, breaking them down into smaller units and representing their syntactic relationships using formal representations, such as parse trees or dependency graphs. Parse trees illustrate the constituent structure of sentences, showing how words group together to form phrases and how phrases combine to form larger constituents. Dependency graphs, on the other hand, represent the grammatical relationships between words in terms of directed links, where each word is connected to its governing word or head. Parsing can be performed at different levels of granularity, including sentence-level parsing, which analyses the structure of an entire sentence, and phrase-level parsing, which focuses on the structure of phrases within a sentence. Various parsing algorithms and models have been developed to automate the parsing process, ranging from rule-based approaches to statistical and machine learning-based methods, including constituency parsing and dependency parsing. CFG stands for context-free grammar, which is a formalism used in parsing and describing the syntax of languages. It is a type of formal grammar that consists of a set of production rules that define how different elements or symbols in a language can be combined to form valid sentences. In a CFG, the grammar rules are defined in the form of production rules that consist of a non-terminal symbol, also known as a variable, and a sequence of symbols, terminals or non-terminals. The non-terminal symbols represent syntactic categories or parts of speech, while the terminals represent actual words or tokens in the language. The production rules specify how these symbols can be combined or rewritten to form valid sentence structures. Definition of parsing. Natural language parser is a program that figures out which group of words go together, as phrases, and which words are the subject or object of a verb. The NLP parser separates a series of text into smaller pieces based on the grammar rules, CFG, CNF. If a sentence that cannot be parsed may have grammatical errors. Different types of parser. In natural language processing, there are various types of parsers used to analyze the grammatical structure of sentences. Here are some commonly used types of parsers. Recursive descent parser. Recursive descent parsing is a top-down parsing technique where a parser starts from the top of the parse tree and recursively applies production rules to match the input sentence. It uses a set of recursive procedures to handle each non-terminal symbol in the grammar. Recursive descent parsers are relatively easy to implement, but may suffer from left recursion and backtracking issues. Shift-reduce parser. Shift-reduce parsing is a bottom-up parsing technique where a parser builds the parse tree by shifting input tokens onto a stack and then reducing the stack contents based on the grammar rules. Shift-reduce parsers operate by repeatedly shifting tokens or reducing groups of tokens until a valid parse tree is constructed. Examples of shift-reduce parsers include the LR, left-to-right, rightmost derivation, and SLR, simple LR parsers. Chart parser. Chart parsing is a dynamic programming-based parsing technique that uses a chart data structure to efficiently explore and combine partial parse hypotheses. It breaks the input sentence into smaller subparts and uses bottom-up and top-down operations to construct partial parse trees. Chart parsing algorithms, such as early parsing and CYK, Koch-Younger-Kasami parsing, can handle ambiguous grammars and produce multiple parse trees. For CYK parsing, we should use CNF grammars instead of CFG. CNF stands for Chomsky Normal Form, which is a standardized form of context-free grammar, CFG. Dependency parser. Dependency parsing focuses on determining the grammatical relationships between words in a sentence. Instead of constructing a parse tree, dependency parsers represent the syntactic structure using directed links between words, where each word depends on another word in the sentence. Dependency parsing is widely used in tasks such as information extraction, relation extraction, and syntactic analysis. Transition-based parser. Transition-based parsing is a parsing approach that involves making a series of transition decisions to construct the parse tree or dependency graph. It uses a set of transition actions, such as shift, reduce, left arc, and right arc, to build the parse tree step by step. Transition-based parsers are often implemented using machine learning techniques, such as neural networks or support vector machines, to learn the transition decisions. A constituency parser. Constituency parsing aims to identify the constituent structure of sentences, representing how words group together to form phrases and larger constituents. Constituency parsers generate parse trees that explicitly show the hierarchical structure of the sentence. Examples of constituency parsers include probabilistic context-free grammar, PCFG parsers, and lexicalized parsers like the Stanford parser. Word embeddings are typically used in the pre-processing phase of NLP tasks. The pre-processing phase involves transforming raw text data into a format that can be readily understood and processed by NLP models. Word embeddings play a crucial role in this phase by representing words as continuous vector representations. Word embeddings capture semantic and syntactic similarities between words, allowing for more efficient and effective processing of natural language text in various NLP tasks. Word embeddings have become a fundamental component of many NLP models and applications. Here are some reasons why and when we need word embeddings. Semantic similarity and word meaning. Word embeddings capture semantic relationships between words. Words with similar meanings or that are used in similar contexts tend to have similar vector representations in the embedding space. This property enables us to measure semantic similarity between words by computing distances or similarities between their embeddings. For example, the cosine similarity between word embeddings can be used to determine how related or similar two words are in meaning. Dimensionality reduction. Word embeddings provide a way to represent high-dimensional and sparse word spaces in a lower-dimensional dense vector space. Traditional approaches like one-hot encoding represent words as high-dimensional sparse vectors, where each dimension corresponds to a unique word. Word embeddings, on the other hand, represent words as continuous, dense vectors of fixed dimensions. This reduces the dimensionality of the word space and allows for more efficient and effective processing of textual data. Capturing word context and relationships. Word embeddings are trained using large amounts of text data, which allows them to capture word co-occurrence patterns and context. Words that often appear together or in similar contexts tend to have similar vector representations. This contextual information is useful in various NLP tasks such as sentiment analysis, named entity recognition, and machine translation, where understanding the relationship between words and their context is crucial. Transfer learning and generalization. Pre-trained word embeddings can be used as initial representations in downstream NLP tasks. By leveraging pre-trained embeddings, models can benefit from the generalization and knowledge acquired from large-scale training data. Transfer learning with word embeddings helps overcome data scarcity issues in specific tasks and improves performance, especially when the task at hand has limited training data. Improved model performance. Using word embeddings in NLP models often leads to improved performance compared to traditional methods that rely on sparse representations. Models that incorporate word embeddings as input features can learn more expressive and nuanced representations of text, capturing intricate relationships between words. This can lead to better accuracy and robustness. Word embeddings and the distributional hypothesis are closely related concepts in the field of natural language processing, NLP. The distributional hypothesis is a fundamental principle that forms the basis for the development and use of word embeddings. The distributional hypothesis states that words that appear in similar contexts tend to have similar meanings. In other words, the meaning of a word is reflected in its distributional patterns within a given corpus. This hypothesis suggests that words with similar meanings are likely to occur in similar contexts and can be treated as interchangeable to some extent. Word embedding techniques are methods used to represent words as numerical vectors in a high-dimensional space. These vectors capture the semantic and syntactic relationships between words, allowing machine learning models to process and understand natural language. Here are some commonly used word embedding techniques. Frequency-based embedding and prediction-based embedding are two broad categories of word embedding techniques. Frequency-based embedding. Frequency-based embedding techniques capture the distributional information of words based on their co-occurrence statistics within a corpus. These methods focus on the frequency of word occurrences and their relationships with neighboring words. Examples of frequency-based embedding techniques include count-based methods. Count-based methods, such as term frequency inverse document frequency, TF-IDF, and pointwise mutual information, PMI, calculate statistical measures to represent word co-occurrence patterns. These methods assign higher weights to words that appear frequently together or have low document frequency. A latent semantic analysis. LSA uses singular value decomposition to factorize a word document matrix and obtain low-dimensional word representations. LSA captures the latent semantic relationships between words by representing them in a semantic space. Prediction-based embedding. Prediction-based embedding techniques utilize machine learning models to learn word representations by predicting some task-related properties of words. These methods focus on capturing the meaning and semantic relationships between words. Examples of prediction-based embedding techniques include the word-to-vec. Word-to-vec is a popular word embedding technique that represents words as dense vectors. It uses a shallow neural network to learn word representations from a large corpus of text. Word-to-vec provides two main models: continuous bag of words, CBOW, and skipgram. CBOW predicts the target word from the context words, while skipgram predicts the context words given a target word. A glove, global vectors for word representation glove, is another widely used word embedding technique. It leverages both global and local word co-occurrence statistics to construct word vectors. Glove training involves factorizing a word co-occurrence matrix to learn word representations that capture word similarities and relationships. Fast text. Fast text is an extension of word2vec that introduces subword information. It represents each word as a sum of character n-grams, subword units, allowing it to handle out-of-vocabulary words and capture morphological information. Fast text is particularly useful for languages with rich morphology. ELMO. Embeddings from language models. ELMO is a contextual word embedding technique that takes into account the meaning of a word within the context of the sentence. It uses a deep bidirectional language model to generate word representations that are context-dependent. ELMO embeddings have been effective in various natural language processing tasks. BERT, bidirectional encoder representations from transformers. BERT is a powerful contextual word embedding technique based on the transformer architecture. It pre-trains a deep bidirectional language model on a large corpus of text and then fine-tunes it on specific tasks. BERT embeddings capture fine-grained contextual information and have achieved state-of-the-art performance in various NLP tasks. Transformer-based embeddings. Apart from BERT, other transformer-based models such as GPT, Generative Pre-trained Transformer, and GPT-2 have also been used for word embeddings. These models learn to generate text and can be used to extract word representations based on their internal states. Both frequency-based embedding and prediction-based embedding techniques have their own advantages and are suitable for different applications. Frequency-based methods are simple and computationally efficient, while prediction-based methods capture more fine-grained semantic relationships. The choice of embedding technique depends on the specific task and the nature of the data being processed. WSD, Word Sense Disambiguation. WSD can be considered both a pre-processing task and a standalone task, depending on the specific application and context. In some cases, WSD is performed as a pre-processing step to disambiguate words before feeding them into downstream NLP tasks. For example, in machine translation or information retrieval systems, WSD may be used to disambiguate words in the source text or query to ensure that the subsequent processing steps operate on the correct sense of the words. In this sense, WSD acts as a pre-processing task that helps improve the accuracy of subsequent NLP tasks. However, WSD can also be viewed as a standalone task when the primary goal is to disambiguate words and determine their correct senses in isolation. Researchers and systems have been specifically developed to tackle the challenge of WSD as an independent task, focusing on the accurate disambiguation of words and providing a comprehensive set of possible senses for each ambiguous word. Therefore, while WSD is often used as a pre-processing step to enhance the performance of downstream NLP tasks, it can also be studied and approached as a separate task with its own set of methodologies and evaluation metrics. WSD refers to the task of determining the intended meaning or sense of a word within a given context. It is a challenging problem in NLP because many words have multiple meanings, and the correct sense of a word often depends on the surrounding words or the broader context. The goal of WSD is to assign the most appropriate sense from a predefined set of possible senses to an ambiguous word. For example, the word bank can refer to a financial institution or the edge of a river. Without proper disambiguation, the intended meaning of the word in a sentence may be unclear. Word sense disambiguation is used in various NLP applications, including machine translation. WSD helps improve the accuracy of machine translation systems by ensuring that the correct meaning of a word is translated accurately. Information retrieval. WSD is used to enhance search engines by understanding the context of a query and retrieving documents that match the intended meaning of the query. Question answering. WSD aids in question answering systems by accurately interpreting the meaning of words in a question and retrieving relevant answers. Sentiment analysis. WSD is beneficial for sentiment analysis tasks, where understanding the correct sense of words is crucial for determining the sentiment expressed in a text. Text summarization. WSD can improve text summarization systems by disambiguating words and generating summaries that capture the intended meaning. Overall, word sense disambiguation is utilized in various NLP tasks to improve the accuracy and effectiveness of natural language understanding and processing systems. There are several approaches and techniques for performing word sense disambiguation, WSD. Here are some commonly used methods. Dictionary-based WSD. This approach involves using dictionaries or lexical resources that provide sense definitions and example sentences. The idea is to match the target word with its various senses listed in the dictionary and select the most appropriate sense based on the context. This method relies on handcrafted sense inventories and can be computationally efficient but may lack coverage and struggle with handling new or domain-specific words. 2. Supervised WSD. In this approach, a supervised learning algorithm is trained using labeled examples where the correct sense is known. These examples typically consist of word context pairs, and the features can include words in the context, syntactic patterns, or other linguistic cues. The trained model can then be used to disambiguate senses in new unseen contexts. Supervised WSD requires annotated training data and relies on the availability of sense-annotated corpora. 3. Unsupervised WSD. This approach aims to perform WSD without relying on annotated training data. It often leverages statistical techniques, clustering algorithms, or distributional similarity measures to group similar word contexts and assign senses based on these groupings. Unsupervised WSD can be useful when labeled training data is scarce or unavailable, but it may be less accurate compared to supervised approaches. 4. Knowledge-based WSD. This approach utilizes structured knowledge resources such as WordNet or other semantic networks. It relies on the hierarchical relationships and semantic relations between words to infer the correct sense. Knowledge-based WSD can involve methods like path-based similarity, Lesk algorithm, or graph-based algorithms that traverse the word sense networks. These methods can be effective in capturing the semantic relationships between words, but may face limitations in handling polysemy or new words not present in the knowledge resource. 5. Hybrid approaches. Many WSD systems combine multiple methods or incorporate additional features to enhance disambiguation accuracy. Hybrid approaches can combine dictionary-based techniques with supervised or unsupervised methods, or leverage external resources like corpus statistics, ontologies, or machine learning algorithms to improve disambiguation performance. The choice of WSD method depends on factors such as available resources, data, and the specific requirements of the application. Different approaches have their strengths and weaknesses, and their effectiveness may vary depending. Feature engineering. Feature engineering is the process of creating or selecting relevant features from raw data to improve the performance of machine learning models. It involves transforming or manipulating the existing data into a format that better represents the underlying patterns and relationships. The motivation behind feature engineering stems from the fact that the success of machine learning models heavily depends on the quality and relevance of the features used as inputs. Well-engineered features can enhance the model's ability to learn and capture important patterns, resulting in improved accuracy, better generalization, and more robust predictions. Here are some key motivations behind feature engineering. Improved model performance. Feature engineering aims to provide the model with more informative, discriminative, and relevant features that can better capture the underlying patterns in the data. By constructing features that encode domain knowledge, relationships, or transformations, the model can have a better understanding of the data, leading to improved performance. Dimensionality reduction. In many real-world datasets, the number of features can be large, which can pose challenges in terms of computational efficiency, model interpretability, and generalization. Dimensionality reduction. Dimensionality reduction is a technique used to reduce the number of features or variables in a dataset while preserving or minimizing the relevant information. It aims to simplify the data representation by transforming it into a lower dimensional space, where each dimension or feature captures meaningful and informative patterns. There are several reasons why dimensionality reduction is needed. Curse of dimensionality. High-dimensional data often suffers from the curse of dimensionality. As the number of features increases, the data becomes sparser, and the amount of available data decreases relative to the feature space. This can lead to computational inefficiency, increased storage requirements, and difficulties in analysis. Dimensionality reduction can mitigate these issues by reducing the number of features while retaining most of the relevant information. Overfitting. High-dimensional data increases the risk of overfitting in machine learning models. When the number of features is large compared to the number of samples, models may become overly complex and capture noise or irrelevant patterns. Dimensionality reduction helps in reducing the complexity of the data, improving model generalization, and reducing the likelihood of overfitting. Computational efficiency. Dimensionality reduction can significantly improve the efficiency of data processing and analysis. With a reduced number of features, the computational cost of various tasks such as training machine learning models, similarity searches, and clustering can be substantially reduced. Noise and redundancy removal. High-dimensional data often contains noise and redundant information that can obscure meaningful patterns. Dimensionality reduction techniques aim to filter out noise and extract the most relevant and informative features, improving the data quality and interpretability. Dimensionality reduction methods can be broadly categorized into two types: feature selection and feature extraction. Feature selection methods directly select a subset of the original features based on certain criteria, discarding the rest. Feature extraction methods, on the other hand, transform the original features into a new lower dimensional space, combining or projecting them onto a new set of features. Commonly used dimensionality reduction techniques include principal component analysis, PCA, linear discriminant analysis, LDA, TSNE, T-distributed stochastic neighbor embedding, and autoencoders. The choice of technique depends on the specific requirements of the dataset and the desired outcome, whether it is to preserve global structure, class separability, or local neighborhood relationships. Dimensionality reduction techniques. Dimensionality reduction methods such as principal component analysis, PCA, and linear discriminant analysis, LDA, can be used for feature selection indirectly. These techniques transform the original feature space into a lower dimensional space by creating new features that capture the most important information. The transformed features can be ranked or selected based on their contributions to the explained variance or class separability. It's worth noting that feature selection should be performed carefully and in conjunction with model evaluation. The selected feature subset should be validated using appropriate evaluation metrics and cross-validation techniques to ensure that the chosen features generalize well to unseen data. Furthermore, the choice of feature selection method depends on the dataset characteristics, the machine learning algorithm being used, and the specific goals of the analysis. There are various methods of dimensionality reduction, each with its own approach and characteristics. Here are some commonly used methods. Principal component analysis, PCA, is a statistical procedure that is used to reduce the dimensionality. It uses an orthogonal transformation to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components. It is often used as a dimensionality reduction technique. Step 1. Standardize the dataset. We need to standardize the dataset, and for that, we need to calculate the mean and standard deviation for each feature. We use mean and standard deviation for data standardization. Step 2. Calculate the covariance matrix for the features in the dataset. Use statistical covariance formula to build the covariance matrix. Step 3. Calculate the eigenvalues and eigenvectors for the covariance matrix. An eigenvector is a non-zero vector that changes at most by a scalar factor when that linear transformation is applied to it. The corresponding eigenvalue is the factor by which the eigenvector is scaled. Going by the same approach, we can calculate the eigenvectors for the other eigenvalues. We can from a matrix using the eigenvectors. Step 4. Sort eigenvalues and their corresponding eigenvectors in the matrix. Step 5. Pick top few eigenvalues and form a matrix of eigenvectors. Step 6. Transform the original matrix using below formula. Feature matrix asterisk top selected eigenvectors equals transformed data with lower dimensionality. Other popular dimensionality reduction techniques. Linear discriminant analysis, LDA. LDA is a dimensionality reduction technique that aims to find a linear transformation that maximizes the class separability. It projects the data onto a lower dimensional space while maximizing the between-class scatter and minimizing the within-class scatter. TSNE, T-distributed stochastic neighbor embedding. TSNE is a nonlinear dimensionality reduction technique that is particularly effective in visualizing high-dimensional data. It focuses on preserving the local neighborhood relationships of the data points, mapping them into a lower dimensional space where similar samples are closer together. ISOMAP. ISOMAP is a nonlinear dimensionality reduction method that preserves the geodesic distances between data points. It constructs a neighborhood graph based on pairwise distances and computes a low-dimensional representation that maintains the geodesic distances as closely as possible. Autoencoders. Autoencoders are neural network-based models that can learn an efficient representation of the input data. They consist of an encoder network that maps the input to a lower dimensional latent space and a decoder network that reconstructs the original data from the latent representation. The latent space serves as the reduced dimensional representation of the data. Random projection. Random projection is a simple and computationally efficient method for dimensionality reduction. It uses random projection matrices to map the data from a high-dimensional space to a lower-dimensional space while approximately preserving pairwise distances between the data points. Feature extraction methods. Other examples for other purposes. Example: extracting edges from images. Image processing, or classifying the images containing face. Features can be extracted from the content of an image, such as color, texture, shape, position, dominant edges of image items. Set of animal photographs which contains face. Raw data is set of pixels. Higher level features are extracted out of it like presence or absence faces or other body parts. Algorithms are used to detect features such as shapes, edges, or motion in a digital image or video to process them. Example: analysis of written texts where we want to extract opinions. Example: bag of words widely used in natural language processing. Here, words or features are extracted from a sentence, document, website, etc. These features are classified according to the frequency of use. So in this whole process, feature extraction is one of the most important part. New feature construction from existing features. Feature construction involves creating new features by combining or transforming the original features based on domain knowledge, insights, or mathematical operations. Mathematical operations include arithmetic operations, e.g., addition, subtraction, multiplication, division, logarithmic transformations, exponential transformations, square roots, or polynomial expansions. Feature construction can involve creating interaction terms, ratios, or differences between features to capture important relationships. For example, in a dataset with height and weight, a new feature called body mass index, BMI, can be constructed by dividing weight by the square of height. Feature construction allows the model to learn complex relationships that are not explicitly present in the original data, thereby improving the model's ability to capture relevant patterns and improve predictive performance. Feature construction also enables the incorporation of domain knowledge, allowing the creation of features that encode specific domain insights. Or another example, mapping data to new space. Example: Fourier transform. The Fourier transform is an important image processing tool. It is used to decompose an image into its sine and cosine components. Input image is in the spatial domain. The output of the transformation represents the image in the Fourier or frequency domain. In the Fourier domain image, each point represents a particular frequency contained in the spatial domain image. The Fourier transform is used in a wide range of applications. e.g., reducing blurring and noise, image filtering, image reconstruction and image compression, such as JPEG format. Both feature extraction and feature construction are important techniques in feature engineering. Feature extraction reduces dimensionality and eliminates irrelevant or redundant features, while feature construction allows for the creation of new features that capture important relationships and patterns in the data. Feature selection. Feature selection methods aim to select a subset of the original features based on certain criteria. They can be based on statistical measures like information gain, mutual information, or statistical tests such as chi-square test or ANOVA. Feature selection methods eliminate irrelevant or redundant features, reducing the dimensionality while maintaining the interpretability of the selected features. It's important to note that the selection of the appropriate dimensionality reduction method depends on various factors, including the characteristics of the data, the desired outcome, and the specific problem at hand. The choice should be made considering the trade-offs between computational complexity, interpretability, preservation of important patterns, and the goals of the analysis. Here are several commonly used methods for feature selection in machine learning. 1. Filter methods. Filter methods rank features based on statistical measures such as correlation, mutual information, chi-square, or variance. Features are evaluated independently of the machine learning algorithm used. High-ranking features are selected based on a predetermined threshold or a fixed number. Examples of filter methods include Pearson correlation coefficient, information gain, and ANOVA. 2. Wrapper methods. Wrapper methods evaluate feature subsets by training and evaluating the machine learning model on different combinations of features. They use the performance of the model, e.g., accuracy, F1 score, as a criterion for feature selection. The search for optimal feature subsets can be performed exhaustively, e.g., using brute force, or heuristically, e.g., using forward/backward selection or recursive feature elimination. Wrapper methods can be computationally expensive, but provide a more accurate evaluation of feature subsets. The examples of wrapper methods include recursive feature elimination, RFE, and sequential feature selection. 3. Embedded methods. Embedded methods perform feature selection as an integral part of the model training process. They combine feature selection and model training into a unified optimization problem. These methods aim to find the most informative features by considering their importance within the model's learning algorithm. Examples of embedded methods include L1 regularization, lasso, tree-based feature importance, such as random forest or gradient boosting, and regularization methods like elastic net. Correlation refers to a statistical relationship between two or more variables, where changes in one variable are associated with changes in another. The correlation coefficient quantifies the strength and direction of this relationship. Positive correlation: if one variable increases as the other increases, the correlation is positive, e.g., height and weight. Negative correlation: if one variable decreases as the other increases, the correlation is negative, e.g., speed and travel time. Zero correlation: no relationship exists between the variables. Chi-square test. This test assesses whether two categorical variables are independent or associated. It compares the observed frequency of occurrences in a contingency table to the frequencies expected under the assumption of independence. The formula for the chi-square statistic is I superscript 2 equals sigma, OE superscript 2/E. Where sigma, summation symbol. O, observed frequency. E, expected frequency. The test statistic follows a chi-square distribution with degrees of freedom based on the number of categories or variables involved. The chi-square test is widely used in fields like social sciences, market research, and biology to test hypotheses about categorical data, such as whether gender is related to voting preference or if a dice is fair. A p-value is computed to determine statistical significance, with a low p-value indicating that the observed data significantly differs from the expected data. P-value is obtained from the chi-square distribution table based on the desired level of significance, alpha, and the degrees of freedom. The degrees of freedom depend on the number of categories in each variable. The desired level of significance, alpha, often referred to as the alpha level, is a threshold that defines the probability of rejecting a true null hypothesis in a statistical test. Kramer's V. Kramer's V is a measure of association between two categorical variables that quantifies the strength of their relationship after performing a chi-square test. Information theory metrics. Information theory metrics are mathematical measures used to quantify the amount of information, uncertainty, and entropy in a dataset or a probability distribution. Information theory metrics are often used in filter methods to identify the most relevant features based on their information content. Here are some of the key information theory metrics. Shannon entropy is a measure of the average amount of information or uncertainty in a random variable. It quantifies the amount of surprise associated with an event or an outcome. Joint entropy measures the average uncertainty or information content of two random variables x and y considered together. It captures the combined uncertainty in both variables. Conditional entropy measures the remaining uncertainty in random variable y given that random variable x is known. It represents the average amount of information needed to describe y when x is already known. And mutual information quantifies the amount of information that two random variables x and y share. It measures the reduction in uncertainty about one variable when the other variable is known. Kuhlbach-Leibler divergence (KL divergence) measures the difference between two probability distributions. It quantifies the amount of information lost when one distribution is used to approximate another. Information gain and Gini index are two commonly used metrics in decision tree algorithms for feature selection and determining the optimal splitting criterion. These metrics help evaluate the quality of a split based on the impurity or uncertainty reduction they provide. Information gain is a measure of the reduction in entropy or uncertainty achieved by splitting a dataset based on a particular feature. Entropy quantifies the impurity or disorder in a dataset. Information gain is calculated as the difference between the entropy of the parent node and the weighted average of the entropies of the child nodes after the split. The higher the information gain, the better the split. Mathematically, information gain is calculated as follows. Information gain equals entropy, parent, sum, weighted entropy, child. Information gain is commonly used in decision tree algorithms such as C4.5 and ID3. A Gini index. The Gini index is another measure of impurity used in decision tree algorithms. It quantifies the probability of misclassifying a randomly chosen element from a dataset if it were randomly labeled according to the class distribution in the dataset. The Gini index ranges from 0 to 1, where 0 indicates a pure node, all samples belong to the same class, and 1 indicates maximum impurity, an equal distribution of samples across all classes. A Fisher score. The Fisher score, also known as Fisher discriminant analysis or Fisher's linear discriminant, is a statistical measure used for feature selection and dimensionality reduction. It aims to find a linear combination of features that maximally separates different classes or groups in a dataset. Fisher's linear discriminant analysis is particularly useful in supervised learning problems where there are multiple classes, and the goal is to find a projection that maximizes the separability between the classes. Calculate the Fisher score. The Fisher score is computed by taking the ratio of the determinant of the between-class scatter matrix to the determinant of the within-class scatter matrix. It represents the separability of the classes based on the chosen features. The features with higher Fisher scores indicate better discrimination power between the classes. These features are selected for further analysis or used for dimensionality reduction. It's important to note that the Fisher score assumes a linear relationship between the features and may not capture nonlinear relationships effectively. Class imbalance. Class imbalance refers to a situation in machine learning where the distribution of classes in the dataset is heavily skewed, with one or more classes being significantly underrepresented compared to others. Dealing with class imbalance is crucial because it can negatively impact the performance of machine learning models, leading to biased predictions and low accuracy for the minority class. Here are several approaches to address class imbalance. B-sampling the dataset. Oversampling. Increase the number of instances in the minority class by randomly replicating existing instances or generating synthetic samples using techniques like SMOT, synthetic minority oversampling technique. A. Undersampling. Reduce the number of instances in the majority class by randomly removing instances or selecting a subset. This can be done using techniques like random undersampling or cluster centroids. A. Hybrid approaches. Combine oversampling and undersampling techniques to achieve a balanced distribution of classes. For example, SMOT combined with Tomek links or SMOT combined with edited nearest neighbors. Class weighting. Modify the weights assigned to different classes during model training. Assign higher weights to the minority class, making it more influential during the learning process. This can be done by adjusting the class_weight parameter in many machine learning algorithms. Threshold adjustment. Adjust the classification threshold to improve the model's performance on the minority class. By moving the threshold, you can prioritize precision or recall based on the problem requirements. Generate more data, or if feasible, collect more data for the minority class to balance the dataset. This can help the model better understand the patterns and characteristics of the underrepresented class. Ensemble methods. Utilize ensemble methods such as bagging, boosting, or stacking to combine multiple models. Ensuring that each model has access to a balanced subset of the data can improve the overall performance on the minority class. Algorithm selection. Choose algorithms that are less sensitive to class imbalance, such as random forests, support vector machines with nonlinear kernels, or gradient boosting. Evaluation metrics. Rely on evaluation metrics that are more informative when dealing with imbalanced data, such as precision, recall, F1 score, area under the precision recall curve, or ROCAUC, receiver operating characteristic area under the curve. It is important to note that the choice of approach depends on the specific problem, dataset, and algorithm being used. It may require experimentation